Yes. So thank you very much for the introduction. So yeah, today I'm here to talk about the formalization of differential geometry with proof of systems, and more specifically in Lean. I actually started with Lean. I also work with Isabel this year a little bit, but I definitely feel more familiar with Lean. So yeah, I will talk about Lean today. So I will start by giving you just a quick overview of what it's like to do differential geometry with proof of systems. And what I want to say here is that doing geometry with proof of systems might feel a little bit harder than some areas of maths sometimes. And this is because sometimes proofs in geometry might be a little bit more sloppy, and details are often skipped, as in there's a lot of stuff in geometry that is routine, but that when one has to do proofs with proof of systems, they have to fill in all the details, and this might be a little bit painful. And also the other thing that geometry has more than other areas of mathematics is that geometry by definition is the most visual area of mathematics, is the one where there is the most imagination. So this has implies that in geometry sometimes proofs rely a bit on the intuition of readers, and you have to fill in some formal details. You have to adapt your proof to a more formal proof when you want to write it with a proof of systems. And finally, a third problem is that sometimes objects in geometry, they can be closer to they can be more understandable for humans, but they carry with them a lot of data, and it's not always clear how to organize and store with this data in proof of systems. The point is that in standard mathematics, you do not have to really store and organize the data. You have to you have it always with you abstractly, but with the proof of systems, you have to organize it some way, and this sometimes has some implication on how you give definitions with proof of systems. So just to have a look at how proof of systems are doing with geometry. So my impression is that most proof of systems are at the beginning with differential geometry. I don't know about any proof of system which has advanced material. Lean is also at the beginning, but it starts to have some solid grounding, some base concepts which are formalized in a solid way. And as far as I'm aware, is one of the proof of systems which is doing the most progress in differential geometry. So I wrote here about two other famous proof of systems that also rely on type theory. So Isabel, for example, which relies on simple type theory, has a formalization of differential geometry that contains most concepts that also Lean has, but for example, it does not have the tangent bundle. And I actually looked into this formalization myself, and I'm pretty sure that it is not possible with the current formalization to formalize the tangent bundle. One has to rewrite a considerable amount of code. So, and Lean actually does have a tangent bundle, so it should not be given for granted. It's a nice thing that Lean has it already. And the other very famous proof of system which relies as Lean on dependent type theory is Coq. And as far as I'm aware, I looked into this a bit, even though I didn't get too much response. Coq does not really have a proper formalization of standard differential geometry, although it has a little bit of synthetic differential geometry. So again, Lean is at its beginning, but is doing some progress. So for what there is now in Lean in differential geometry, we have a smooth manifold with corners over an arbitrary non-discrete norm field, and I'll come to the definition of this in a moment. There are tangent spaces and the tangent bundle. Again, the tangent bundle it should not be given for granted. It's nice that it's there. We have smooth maps and diffeomorphism, partitions of unity. There is the definition of V groups, and there is a slightly unusual implementation of early algebra. I should formalize another implementation soon. Then as for instances, we have this here. As far as I'm aware, we do not have yet projective spaces that Isabel has, but it should not be that complicated to formalize. And there is a primitive version of the Whitney bending theorem. That is to say, it's formalized for a compact manifold without any optimal dimension, but it's already some result that is there. And also I would like to mention quickly what's gonna be there soon. I worked in differential geometry again in the last month, and I should push myself soon. Smooth fibers and vector bundles. As a corollary of this, we should have the cotangent bundle. Always thanks to vector bundles, we should have vector fields and differential forms. With vector fields, I should give the standard definition of Lie algebra of a Lie group, and hopefully, if I'll be able to formalize tensor fields, we should have we should be able to give a definition of Riemannian manifolds. So in the next minutes, I would like to just give you an overview of how manifolds are implemented in Lean in order to talk about more advanced stuff later. So manifolds have been formalized by Sébastien Guezel, that talked just before me, and they are defined in a very general context. As I mentioned before, they are smooth manifolds with corners over an arbitrary non-discrete norm field. So just to quickly go over the definition of, remind what a non-discrete norm field is. So a field is a norm field if it has a real valued map for which that satisfies a couple of conditions that are a triangle inequality for the addition and for which the norm of a product is equal to the product of the norm. Just a quick remark, I usually call this map a valuation, but and I call a norm the same thing, but with an inequality in the product. But apparently this convention is used in analysis, and this convention was used in Lean. And a norm field is said to be non-discrete if there's an element of norm less than 1 or equivalently more than 1. And the idea is that you can get as close to 0 as you want. So that's why it's called non-discrete. So the nice thing about having manifolds over an arbitrary norm field is that you can give the definition of real and complex manifolds in one shot at the same time. And also this covers the definition of periodic manifolds. I don't really know a lot about that, but for people who work in the field, that's nice. And so another concept that we need to mention in order to talk about smooth manifold with corners is that of a model with corners. Personally, I never heard about this concept before approaching Lean, but it's just a slight generalization of the more of standard manifold with corners. So it's not that complicated to get used to it. So a model with corners is just a topological embedding of a topological space into a vector space in such a way that the image of this embedding is nice, as in it satisfies a technical condition that allows the differential of functions defined on this image to be unique, and this allows to talk about smoothness. And the point of model with corners is that they are the most general concept that allows us to talk about smoothness of maps on a vector space and then on manifolds. We do not need to have maps defined on the whole vector space, but just on a nice subset or equivalently on a nice embedding of the vector space into the, sorry, of the topological space into the vector space. Also, the last concept we need is that of a sharded space. This is just a generalization of a manifold. The term might not be that familiar, but it's nothing new really. So a charted space is a topological space which has an atlas of charts that are valued in a fixed model space. So for charts, we mean just local homomorphisms that are what probably the listeners think. So they're just homomorphisms which are defined on a subset of our topological space to a subset of a model space. There is actually some technical problems in defining local homomorphisms. It's not that straightforward, but I do not really have the time to mention them now. At this point, we can give the definition of a smooth manifold with corners, which will be defined as a charted space over a topological space that has a model with corners into a model vector space over our arbitrary non-discrete norm field. And we also require that the change of coordinates are smooth with respect to the model with corners. By change of coordinates, we mean, as classically in geometry, the composition of charts together with the inverse of other charts when the charts have intersect on a common domain. The point is that this change of coordinates are maps that go from our model topological space, or from our model space to the model space, and then we can pre-compose it and compose it with the inverse of the model with corners and with the model with corners, so that we actually get a map from a subset of a vector space to a subset of a vector space, and we can talk about smoothness of this map. So from smooth manifold with corners, we can furthermore extend smooth monoids and Lie groups. So this is done in standard way. We have also a group structure on our manifold, and we also require that the multiplication as a map from the product manifold to the manifold is a smooth map, and that the inversion map is a smooth map. So the formalizing Lie groups is quite standard. We only met one problem in the formalization of Lie groups, and this problem has to do with the fact that one might want to formalize Lie groups to be manifolds without borders. One might want not to deal with borders. This is because there is a theorem that says that if you allow Lie groups to have corners, to have borders, you actually can prove that it does not have borders. So one might want in the first place to forget about model with corners and use a trivial model with corners, that is to say the identity map from the model vector space to the model vector space. However, there is a problem with this, which is which comes from type theory, from the theory underlying Lie. And the problem is that if you ask Lie groups to have the trivial model with corners, then you will not have that Lie groups are stable under product, because the product of two Lie groups, being it a Lie group, will also have to have the trivial model with corners, so the identity map. But the product of two manifolds is defined to have the product of model with corners, which is just the product of the two maps underlying the model with corners. So in this case, it would have the product of two identity maps. And unfortunately, it happens that the product of two identity maps is not definitionally equal to the identity map. So Lie cannot know that the two things are the same, and it is not possible to define Lie groups directly with the trivial model with corners. So you have to actually a bit awkwardly allow Lie groups to have borders. For people that are not that familiar with what definitionally equal means, as you can imagine, definitionally equal means that the two types or two terms are equal by definition. The remark about this is that this is often not the case. Like in many times you need a proof to say that two types or two terms are equal, and a common problem in Lie, in proof assistance that rely on type theory, is that you cannot, you don't have two types that are two types that are not definitional. The proof assistance cannot know that two types are definitionally equal, and sometimes you have no way to tell it that two types are definitionally equal. So the next thing I would like to talk about is vector bundles, which is also something we formalized, and vector bundles are also a nice case because they are not that trivial to formalize. There are some choices that need to be done, and yes, and that's it. So yeah, actually, yeah, the other thing I wanted to say is that they also show some problems that arise with type theory that do not arise in standard mathematics. So I will start by quickly reminding the definition of vector bundles, also to fix definition. So as per the definition of the vector bundle, we considered the standard modern definition of a vector bundle, which is the one that you can find on Wikipedia or on most modern geometry books. So it is the most straightforward definition. It's probably the one that is better formalized. So we have a vector bundle is given by two topological spaces and a projection, which is a continuous projection from one topological space to the other. Then we have a structure of vector space on the fibers of our projection and a model vector space. This is the data of a vector bundle, and all this data satisfies some standard condition that you can find basically everywhere that I have not the time to go through now. There are many possibilities when it comes to formalizing vector bundles, but there is one choice which is closest to this definition, one choice which is more literal than other choices, and it consists in basically reproducing this definition word by word, translating things in type theory the simplest way. And indeed, we start with two topological spaces in Line. We start with our projection, and we put an instance of vector space on the fibers of a projection which are meant to be the preimages of the points in the base space of a projection. And in order to do this, we just quantify we just quantify over the base space when we put our instances, and we have the data that is required by the definition. Then we given a model fiber, we can define trivialization in basically the same way as in standard mathematics, and we can then give a definition of vector bundles directly. So this definition, I went through this definition myself, and it's definitely doable to formalize things this way. This definition, though, has a problem, and the problem is that it is not that natural from the point of view of type theory. Although, again, things are definitely doable this way, there are better definitions. And the problem is that, so at the moment that we formalized vector bundles, the tangent bundle was formalized as the product of the base manifold with the model vector space of the manifold, and this product was then given a topology and a manifold structure so that it was made into the tangent bundle. And the tangent space at each point was defined to be the model vector space, was definitionally equal to this model vector space E. And the problem with the previous definition of vector bundle was that in a case like this, the tangent space at each point would have not been definitionally equal to the fiber of a projection. The fiber of a projection was the preimage of a point in the base space, which was therefore a set of type the total space of the same type as the total space, and this was not could not be definitionally equal to the tangent space at each point. And this was actually not a problem only for the tangent bundle, but would have been a problem for most vector bundles, because we expected most vector bundles to be implemented in terms of sigma types. I'll come to the definition of this in a moment. And the defining vector bundles with sigma types presented exactly the same problem. So for a vector bundle defined that way, you would have had that the true fiber at the point would have not be definitionally equal to the pre-image of a projection. So for people who are not that familiar with type theory, and I will just quickly say that a sigma type is a dependent type, which is analogous to a product, but where the type of the second factor is allowed to vary, and it varies depending on the first factor. So this is a natural type to use for formalizing vector bundles, because the idea is that you have in the first factor the base space, and the fibers, the sigma types pastes together all the fibers, and you have at each point of the base tape of the base space a different type, which is the fiber at that specific point. So the point was that not all vector bundles must be implemented this way, but basically all vector bundles can be implemented this way, and most vector bundles would have probably been implemented this way. And the idea to solve the problem of the first implementation was to think about another implementation of vector bundles where we actually use this fact that most vector bundles would have been implemented through sigma types, and to actually ask to put a constraint on the form of a vector bundle, and to actually ask that the vector bundle is formalized as a sigma type. So the idea behind this is to have a map that goes from the base space into a universe of types, and for each point of the base space gives the fiber at that point, and to talk about vector bundles through this map. From this map contains all the data, and from this map you can reconstruct the total space and the projection of the vector bundle. And the idea is that you want to talk about vector bundles which are formalized in this way through this map. You want to restate the theorems you have on vector bundles instead of using the total space and the projection by using this map. This might be a little bit annoying at the beginning because one might be used to the standard language of the total space and of the projection, but it's definitely something which gets little time to get used to. After a couple of statements, you get into this logic, and it's not that hard to pick it up, and it allows to solve the problems that we had before. The reason why it solves that problem is that now that we have this constraint, this strong constraint, we will always talk about the fibers of vector bundles through this map, and we will not need anymore to use the projection and the pre-images of the projection. I want to remark that it is still the case that the pre-images of the projection are not definitionally equal to the fiber given by this map, so E of X in this case. But this is not anymore a problem, because indeed we have this very strong constraint, and we have another standard way to talk about the fibers, and we can forget about the projection. We basically don't need to talk about the projection anymore. We only need the projection in order to recognize a vector bundle as a fiber bundle, but we avoid it in most statements. And this is basically the end of the talk, at least of the mathematics part. I just wanted to add a couple of announcements, and I wanted to say that the paper should be soon available on the archive and in the conference proceedings, and that actually I was able to only talk about less than half of the material on the paper. On the paper, there's way more material and way more details. So I encourage whoever is interested in differential geometry with proof assistance to have a look at it. And yes, that's it. Thank you for listening.
Okay, thank you. We have time for maybe one or two quick questions. I see, well, Kevin Buzzard is writing. Maybe, Kevin, you should ask it directly.
I can read it.
Okay.
Yeah, linear algebra on bundles.
Yes, this is I'm doing this in this precise moment. So
great.
I'm formalizing. I basically finished today to define the direct sum of two vector bundles. As for tensor product, I'm not that familiar yet with the tensor products. How are tensor products formalized in linear algebra? But I think it should be definitely doable. I formalized.
I think if you can do direct sums, you can probably do tensor products.
Definitely. I formalized recently a new construction of vector bundles that it should allow to put a topology on the total space starting from the charts, and I expect to use this a lot in this kind of construction. And yes, I think in the next month or so we should have all these kind of constructions.
That's absolutely great.
Yes. And thanks.
Oh,
sorry, go on.
I just wanted to say there's a question by Emmanuel, but if you want to continue.
Yeah, I just wanted to add that we should also have sections soon, and thanks to section, we should also have like thanks to tensor product and thanks to section, we should have tensor fields and so differential forms and stuff like that. So the question by Manuel, he wrote it above. Okay.
No, he just raised his hand, so he's going to speak.
It's the thing that I also wrote.
So you wrote it.
Is there anything that speaks against being able to do this in Isabelle?
About what? Vector?
Manifolds with corners.
Oh, no, I don't think there's actually a problem for manifolds with corners. It's just that they were not, I don't know, the people who formalized smooth manifolds started with manifolds without borders.
Well, probably, I think that was because they didn't know how to do manifolds with corners.
Oh, okay.
So that's actually has been a discussion with a few people here in Munich. So we always wanted to have this somehow, but none of us knew how to do this. So it would be really nice to have this.
In Isabelle. I didn't look into how to do manifold with corners in Isabelle. I looked into the tangent bundle a lot, but yes, I don't know if there's a very fundamental problem.
Yeah, I recall that Fabian, who did the smooth manifold, said that tangent bundles in simple type theory were quite painful.
Yes, actually, I think there is a way which is not that painful, but the point is that we should, like in Isabelle, we should use the library, the topology library, abstract topology, and people should avoid to use type classes at all.
Mm-hmm.
It's basically impossible to do that with type classes, but with abstract topology, it is possible.
Okay.
Okay, one last question by Anthony.
Oh, yeah.
Maybe. He's raised his hand in any case.
Yeah, see, I can see.
But maybe he wanted to comment on something.
Yeah.
Oh, yes, sorry. So yeah. It was not a question, but it's a reaction to Manuel's question. I think there is any problem in doing all these things in Isabelle, but I think the current implementation of smooth manifold in Isabelle is not done at the right level of abstraction. So I think we can't expect that the library will be scalable, probably. And I think it should be redone in a different way, probably in a more abstract way.
Well, then I hope somebody will do it.
By the way, to answer Eric's question that he wrote on the chat, so he asked if in the expression in slide 17 should be sigma x e of x and not sigma x e. Well, I think in slide 17, if I recall correctly, what I was trying to say there, I did not explain it well by talking, was that I don't know if I can share the screen. The tangent bundle was changed from a product into a sigma type. And in this case, it was a constant sigma type. A product and, well, as Eric knows, a product and a sigma type are not the same type, but they're equivalent types. And that specific sentence was there to say that you can redefine the tangent bundles in terms of the sigma type by using a constant sigma type. So in that case, E is, yes, that's E is constant. So there's not an X after that.
Okay, so thanks for this clarification. So I think we'll go to the coffee break now. So let's thank the speaker again.